Alrighty, folks. So today we're talking about section 4.5. We're taking a brief detour from all this talk about what our derivatives say about what the graph looks like to talk about L'Hopital's rule, which is a very useful and very wonderful tool for finding limits, right? So L'Hopital's rule says that if f of x and g of x are differentiable and f of a equals equals g of a equals 0, and the derivative of g is not equal to 0 for x not equal to a, then the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f prime of x over g prime of x. Right? So one thing to notice here is that other than saying that we are able to find the derivative, and we don't wind up with always having 0 on the denominator, this could be rephrased to say that if, when you substitute in, you get the indeterminate form 0 over 0, then you can use L'Hopital's rule and take the derivative of the top and bottom separately. Right? So that's another thing I want to emphasize. We're not taking the derivative of the whole thing, because that would require us to use quotient rule, and there's no quotient rule involved in this statement. Right? We're taking the derivative of the top and the derivative of the bottom and plugging them straight to the top and the bottom. Right? No quotient rule shenanigans in that part of it. Right? So, but one thing with this indeterminate form, you can use the same tricks we had before to turn other indeterminate forms into 0 over 0 than L'Hopital's. Right? So before, if we had an indeterminate form that was 0 over 0, we could factor and cancel and hope that we got a better thing to take the limit of. Right? If it wasn't 0 over 0, if it was something like 0 times infinity or infinity minus infinity, then we could manipulate it until it was 0 over 0, then we could factor and cancel. Right? So now we have the same sort of idea for L'Hopital's rule. We can use L'Hopital's rule if it's 0 over 0, and hope we get a better thing to take the limit of. Maybe we have to take L'Hopital's rule again. Maybe we have to factor and cancel the next time. Whatever we need to do. And if we're not 0 over 0, we can use those exact same tricks that we used before to make it look like a 0 over 0, and then we can use L'Hopital's rule. Just like we could make it look like 0 over 0, and then we could factor and cancel. Right? So we're in the exact same type of problem, except now we can do things that aren't factorable, but are derivable. Right? There's an expansion to this as well. So if x is going to infinity instead, then we can use L'Hopital's on 0 over 0 or infinity over infinity indeterminate forms. right? So if we get an infinity over infinity and x is also going to infinity, then we don't have to worry about doing any sort of manipulation. We can just use L'Hopital straight out of the box. And that brings the other definition in this section, which is defining growth. And so that is if the limit as x goes to infinity, and this really should be plus or minus, and this should be plus or minus, and this should be plus or minus. But for this case, we're specifically talking about plus. That's why I remembered here's, because this one is specifically just plus. So if as x goes to infinity, f divided by g goes to infinity, then f of x grows faster than g of x, right? So this symbol here means grows faster than, right? And it's exactly what it sounds like. It's like if you're going along at the same pace, f is going to get bigger faster than g of x is, right? If the limit as x goes to infinity of f of x over g of x is 0, then g of x is the one growing faster than f of x, right? If it's going to something other than that, then they're growing approximately the same. We don't really have a symbol for that. But if it goes to like 2 or 5 or -1, then they're growing at approximately the same speed. So that's all of our rules and definitions out of the way. So let's do some problems. Let's find the limit as x goes to 1 of x e to the x plus 2x minus e to the x minus 2 all over sine of 2 pi x, right? And if we substitute, we get e plus 2 minus e minus 2 all over sine of 2 pi, which is 0 over 0. So clearly we're in a situation where we can use L'Hopital's rule. I probably wasn't going to make the first problem be one that we don't have to use L'Hopital's rule, so we might have been able to guess that without substituting, but having our first step be substituting is a good idea just in case, because we don't always know that we're working on a problem from this section. Right? So, L'Hopital's says to take the derivative of the top and bottom and keep the limit part the same. Right? So the derivative of the top, let me get some space. We're going to want to take this guy. Most of this derivative is easy. The first part's a little bit tricky. So if we take the derivative of this, we've got to use the product rule on this first piece. So this first piece is going to be the first times the derivative of the second plus the second times the derivative of the first. So all of this comes from taking the derivative here, plus 2 minus e to the x minus 0. All right, so this is x e to the x plus e to the x plus 2 minus e to the x. So we get x e to the x plus 2. All right, because those guys cancel each other out. And if we take the derivative of the bottom, we're going to have to use the chain rule. So the outside is sine of x. The inside is 2 pi x. If we take the derivative, we get cosine x, and we get 2 pi. Right, so this becomes the derivative of the outside with the inside plugged in times the derivative of the inside. So L'Hopital says that the limit of this original thing that we care about equals the limit if we replace the top with its derivative and we replace the bottom with its derivative. Right, so now we try substituting again, and we get e plus 2, that's promising, that's not 0, 2 pi times cosine of 2 pi, so we get e plus 2 over 2 pi. Right, so that is perfectly viable. So that's what our limit equals. All right. And that's as simple as it gets. You just take the derivative of the top and the bottom, and you're good to go. So another problem. Show that ln of x grows slower than x squared. Right, so this means taking the limit as x goes to infinity, and we can choose here which we want to put on the top and which we want to put on the bottom. Right, it just means, it just changes how we interpret the results. Right, so let's go ahead and put natural log on top and x squared on the bottom. Right, when we plug in, we get infinity over infinity, which means that since x was going to infinity, we're allowed to use L'Hopital's rule. So we want to take the derivative of, these are simple enough, I'm not going to lay it out. So this is equal to the limit as x goes to infinity. The derivative of natural log is 1 to the x, right? That's one of the ones that we should just have. The derivative of x squared is 2x, right? So we can simplify this to get the limit as x goes to infinity of 1 over 2x squared, right? So that's the limit as x goes to infinity of 1/2 x to the negative 2. And if I recall my infinite limit behavior of power functions correctly, that goes to 0, right? Because we've got a negative power up there. So if the function, or if the limit goes to 0, right, we go back to our rule up here. If the limit goes to 0, then the one on bottom is bigger than the one on top. So the limit goes to 0 says that x squared grows faster than ln of x, which is the same statement as ln of x grows slower than x squared. Right, so there we go. Right. So I want to do this last problem because I'm not sure I did one for this type of indeterminate form before. Right, it's one of the things we could have done, though not nearly as easy. Most of the good examples of this really need L'Hopital's rule rather than factor and cancel. But we'll go ahead and do one now. And of course, I may have done one in the problem sessions that are in the future. But the past for you, it's really weird recording these ahead of time. But we can have something that looks like this. Right, so if we substitute in, then this is 1 to the infinity. Right, because secant of x has an asymptote at pi over 2. So when I plug 1 into that, I get secant of pi over 2, which goes off to infinity, right? So this is one of our indeterminate forms, so we've got to do something to it to be able to use L'Hopital's rule, right? So the trick that we're going to use here, right, that came up in the last section, though I'm not sure if I did an example of it, is that e to the limit of the natural log of a function is equal to the limit of that function, right? So sometimes when we can't find the limit of the function, we might be able to find the limit of the natural log of that function, right? And if we do find this limit, then we can put it on top of an e, and we get back the limit that we wanted, right? And this is particularly good for 1 to the infinity indeterminate forms and 0 over 0 indeterminate forms. Both of those indeterminate forms behave much nicer with the limit of the natural log of the function. So the limit as x goes to 1 of ln of x to the secant pi x over 2. We can use our logarithm rules to bring that power to the outside. Right now when we plug it in, we see this goes to infinity times 0. Right, so it's still not infinity, or it's still not 0 over 0, which is what we really want. But we might remember the trick for that is to take one of them and put its reciprocal on the bottom. Right, because dividing by the reciprocal is the same thing as multiplying by the something. And I could have chosen either, right? I could have put the reciprocal of natural log on the bottom. The reason why I chose the trig function is because trig functions' reciprocals have a name, right? So I can simplify this a lot easier and make it look like natural log over cosine of pi x over 2, right? And now this guy's finally going to 0 over 0 when we sub in. So now we can finally use L'Hopital's rule, right? So that means I need to take the derivative of the top and bottom. When I take the derivative of natural log, I get 1 over x. Cosine, this is another chain rule, a lot like the sign we had above. So it's going to be the derivative of the outside with the inside plugged in times the derivative of the inside. Right? And so now I'm going to substitute, and I'm feeling pretty confident with it, so I'm just going to put my equal sign there. All right, 1 over 1, negative sign of pi over 2 times pi over 2. 1 over 1 is just 1. Sine of pi over 2 is at 1. So this is negative pi over 2. And again, dividing by the reciprocal is multiplying by the original thing, and vice versa. So this becomes negative 2 over pi. Right? Now that was the limit of ln of the thing I care about. So if I want to use this rule here, I then have to say, well, limit as x goes to 1 of just the thing that I care about is equal to e to the limit of ln of the thing that I care about, which we just figured out was negative 2 over pi. So the actual limit of the thing that I care about is e to the negative 2 over pi. Right? So that got in a lot of different tricks we can use to substitute things, right? If we have 0 over 0, or as in our case, 1 to the infinity, 0 to the 0, or 1 to the infinity, we can use this natural log trick, right? If we have a 0 times infinity, then we take one of those factors, right? For L'Hopital's rule, you're going to want to take the one that goes to infinity, right? I said it was because this was a trig function, and that's why I was thinking of it, but it's also, for L'Hopital's rule, according to our book, we want it to be 0 over 0. So we take the thing that's infinity and we put its reciprocal on the denominator, and then we know we're going to have 0 over 0. Then we can take derivative of the top and bottom, like we did here. Then, right, I was being pretty daring here. I probably should have tried substituting first, but I was pretty sure it was going to work out. Sometimes you have to do L'Hopital's rule twice, though, right? So don't assume that just because you did L'Hopital's rule once that you're done and finished and everything's going to work out hunky-dory. You do still need to check and make sure. But in our case, we only needed to use it once. All right. So next time we're getting back to what does the derivative say the graph looks like. We're going to learn some tricks for sketching it. So I'll see y'all then.